6.4. The wave behavior of matter. In the years following the development of Bohr's model for the hydrogen atom, the dual nature of radiant energy became a familiar concept. Depending on the experimental circumstances, radiation appears to either a wave or a particle photon character. Louis de Broglie, who was working on his PhD thesis in physics at the Sorbonne in Paris, boldly extended this idea. If radiant energy could, under appropriate conditions, behave as though it were a stream of particles, could matter, under appropriate conditions, possibly show the properties of a wave? Suppose that the electron orbiting the nucleus of a hydrogen atom could be thought of as a wave, with a character wavelength rather than a particle. De Broglie suggested that as the electron moves about the nucleus, it's associated with a particular wavelength. He went on to propose that the characteristic wavelength of the electron or of any other particle depends upon its mass and upon its velocity, where h is Planck's constant. Lambda is h over mv, or wavelength is Planck's constant over momentum. The quantity mv for any object is called its momentum. De Broglie used the term matter waves to describe the wave characteristics of material particles. Because de Broglie's hypothesis is applicable to all matter, any object of mass m and velocity v would give rise to a characteristic matter wave. However, equation 6.8 indicates that the wavelength associated with an object of ordinary size, such as a golf ball, is so tiny as to be completely out of the range of any possible observation. This is not so for an electron, because its mass is so small, as we see in sample 6.5. Within a few years after de Broglie published his theory, the wave properties of the electron were demonstrated experimentally. As electrons passed through a crystal, they were diffracted by the crystal, just as X-rays are diffracted. Thus, a stream of moving electrons exhibits the same kind of wave behavior as electromagnetic radiation. The technique of electron diffraction has been highly developed. In the electron microscope, for instance, the wave characteristics of electrons are used to obtain images at the atomic scale. This microscope is an important tool for studying surface phenomena at very high magnifications. Electron microscopes can magnify objects 3 million times, far more than can be done with visible light, which is 1,000 times. Because the wavelength of electrons is so small compared to visible light. Figure 6.15 is a photograph of an electron microscope image. The uncertainty principle. The discovery of the wave properties of matter raised some new and interesting questions about classical physics. Consider, for example, a ball rolling down a ramp. Using the equations of classical physics, we can calculate the ball's position, direction of motion, and speed at any time with great accuracy. Can we do the same for the electron, which exhibits wave properties? A wave extends in space, and therefore its location is not precisely defined. We might therefore anticipate that it is impossible to determine exactly where an electron is located at a specific time. The German physicist Werner Heisenberg proposed that the dual nature of matter places a fundamental limitation on how precisely we can know both the location and the momentum of any object. The limitation becomes important only when we deal with matter at the subatomic level, that is, with masses as small as that of the electron. Heisenberg's principle is called the uncertainty principle. When applied to the electrons of an atom, this principle states that it's inherently impossible for us to know, simultaneously, both the exact momentum of the electron and its exact location in space. Heisenberg mathematically related the uncertainty of the position, delta x, and the uncertainty of the momentum, delta mv, to a quantity involving Planck's constant. A brief calculation illustrates the dramatic implications of the uncertainty principle. The electron has a mass of 9.11 times 10 to the negative 31 kilograms and moves at an average speed of 5 times 6 meters per second in a hydrogen atom. Let's assume that we know the speed to an uncertainty of 1%. That is, an uncertainty of 0.01 times the speed, and that this is the only important source of uncertainty in the momentum. We can then use equation 6.9 to calculate the uncertainty in the position of the electron, 1 times 10 to the negative 9th meters. Because the diameter of a hydrogen atom is only about 1 times 10 to the negative 10th meters, the uncertainty is in an order of magnitude greater than the size of the atom. Thus, we have essentially no idea where the electron is located within the atom. On the other hand, if we were to repeat the calculation with an object of ordinary mass, such as a tennis ball, the uncertainty would be so small that it would be inconsequential. In that case, m is large and delta x is out of the realm of measurement and therefore has no practical consequence. De Broglie's hypothesis and Heisenberg's uncertainty principle set the stage for a new and more broadly applicable theory of atomic structure. In this new approach, any attempt to define precisely the instantaneous location and the momentum of the electron is abandoned. The wave nature of the electron is recognized, and its behavior is described in terms appropriate to waves. The result is a model that precisely describes the energy of the electron while describing its location, not precisely, but in terms of probabilities.